Hello everybody and welcome. This is our flagship event. It's our Q&A for AI at UCI. We thank you for taking the time to come and be with us, and we really thank our distinguished panelists for taking the time out of their busy schedule to be with us today. So how's this going to work? We have a few questions. So when you signed up, we took the most common ones, and we'll start with those. And then we're going to open up and field questions from you guys. So we have a mic going around, and you can ask all the questions you want. So to give enough time for that, we're just going to jump straight into some introductions so you guys know who you're talking to. First off, we have Forrest Agostinelli right over here. He's a PhD candidate at UCI, currently working in Pierre Baldi's lab. His research involves applying deep learning to problems in natural sciences and reinforcement learning in planning problems. And if you've ever taken CS171, it's the best CA you'll ever have, so welcome, Forrest. Next up, we have Abe Stern. Solutions architect at Nvidia. Abe's background is in computational chemistry, and he is a postdoc here at UCI, working in Doug Tobias's lab, focusing on understanding condensed phase interfaces using classical and quantum molecular dynamic simulation. At Nvidia, Abe focuses on helping university researchers at the intersection of AI and high-performance computing. His current position involves the development of generative models for chemistry. So thank you, Abe.
All right, next we have Nick Navaroli from Google. He graduated from UCI with a master's in 2011 and a PhD in 2014. His thesis focused on applying machine learning methods for analyzing different aspects of email behavior. And he had 2 summer internships at Google before joining in Irvine, at the Irvine office as a full-time senior software engineer. Next we have Professor Samir Singh. He is an assistant professor of computer science at UCI. He is working on large-scale and interpretable machine learning applied to information extraction and natural language processing. And he interned at Google, Microsoft, and Yahoo. We also have Naveen Kumar. He is currently working at Disney Research in LA. He received his PhD in electrical engineering at USC. And his research interests lie in the field of signal processing and machine learning for speech, multimedia, and multimodal applications. All right, so for the first common question, how do you get started in machine learning in industry or research?
I was hoping I would have been first. So my involvement with, so first I'll say my involvement with ML is fairly narrow and scope. I went to UCI here with a graduate degree in machine learning, went straight to Google. I haven't worked elsewhere, so my experience I'll share with you guys is pretty narrow in that regards. But I'll say for starting on the ML, UCI is a great place to go. If you're interested in the program here is great. If you're not in the program or you're thinking about it, there's lots of resources online to kind of get you acquainted with different AI concepts, ML models. I think I forget what they're called, but maybe like Coursera might be one. This was before I or after I graduated, so I'm not too sure. I've heard about it, so there's definitely a lot of resources out there that give you nice tutorials on, what are the core concepts of AI and machine learning, and give you nice example problems, kind of give you a feel for, how do you look at data, how do you model it. So I would say those will probably be the, pretty good resources. I'm sure the other people here will have other great advice as well.
Hi. I started machine learning actually from a signal processing point of view. So I was interested in looking at speech and audio, music signal processing, and started from there. And back in the day when I started my PhD, this used to be actually called statistical modeling. It was kind of all under one big basket of machine learning. So most of the work I did in speech processing was during my PhD at USC. And since then, the field has evolved a lot, and now you're more likely to hear the terms AI and ML, but it kind of starts from the background of statistical learning and basically extending that to current neural network architectures that you look at. So that's kind of my background in ML.
I think I also have a bit of a circuitous path to machine learning. I came at it from the sciences, computational chemistry. So it's a computational science discipline, and I think that background in working with data, the theory background, the math background, and programming kind of came together with personal interests that I had in machine learning. And, when I was in grad school, I started to hear about these things called neural networks and thought, what on earth is that? And I mean, this is back in 2005. It might be difficult to relate to not knowing what a neural network was, but in 2005, I think they were not as widely known as they are now. And essentially, my foray into it was coding up a neural network in C. I got some dusty book from the library. And, after thousands of lines of code, I had what is now possible with about 5 lines of Keras. Continued through grad school and through postdoc with kind of aggressively trying to amass knowledge in statistics and sort of related tasks. I was certainly coming at it through chemistry, so my focus was mostly on quantum and classical simulation, but always with an eye towards how the theory I was learning was more broadly applicable, and seeing these different statistical methods, machine learning methods from a wide variety of perspectives, I think was powerful. Eventually, I now have a role which is not a pure machine learning, not a pure research role, but in a balance of some, I'd say maybe applied research, 50% applied research, and customer support type of roles, helping customers get started. I teach some classes on accelerated computing and introductory machine learning. So that was my foray into industry with machine learning.
Basically, I just wanted to say, if you have a laptop and it has a GPU, you can get started fairly quickly. If you hear about something on the news or read about a paper you saw, you think, oh, that's cool. Oftentimes, people put their code up on GitHub, and nowadays, if you have, Python and you know how to do like, pip install, whatever this is, you can actually get it to work, in a couple of hours, and then, you may not know everything what's going on, but you can twist some knobs and see what's happening and make it do something different. And it doesn't take too much effort. Even when I was doing it in 2012 to get somebody else's code to work, you had to it was like a real pain. But nowadays, if you just have a laptop and a GPU and you think something's cool, if they have their code up on GitHub, the fastest thing to do is just download it, mess around with it, and go from there.
Oh yeah, so that's really good points by Forrest and Nick about how much stuff is available out there. I just want to, as being a contrarian on the panel a little bit, that does come with some downfalls as well, I think, from downsides. I think one of the problems is that it sometimes gives you a false sense of ability of being able to do machine learning. So I think what's important is not to forget what the fundamental mathematical background is that you need for machine learning. And specifically, if you want to test yourself as to what you can do, I would say pick something that you're passionate about. Maybe you like board games, or you like anime, or you like some social sort of thing that you really, really care about or angry about that's going on. Try to gather some data set, try to figure out, is there a machine learning problem you can formulate around it? And then, yes, use all the code, all the material out there, but just try to do something a little bit unique, something that nobody has done exactly, and just try to push yourself a little bit more than what's available out there. And in that process, also contribute to what's out there.
Awesome, thank you. Okay, our next one. What does a typical day look like for you at your job?
Establish the order.
Yeah. Let's see. So it varies quite a bit for me. But I think the general things for me at work, so little context of what I work on at work, I'm a team lead for the search quality side of support.google.com. So as you're searching through that web page, the results you see is, you don't like what's on there, you can blame me for that. So that's what I work on. And so in that aspect, there's a lot of ML that we do behind the scenes that the users don't see. And I spent a good part working with a couple people on the team trying to figure out how can we improve our models, trying to think how can we improve it both in terms of like the features that we use of the support requests that we get coming in. How can we tailor different search results for different types of users? So not only do we have public clients that go to support.google.com, but you're yelling at someone on the phone for a refund on something, the people you're talking to on the phone, they use a bunch of software that goes through our systems as well. So, we have lots of different ML problems that we tackle. So I spend, probably a couple hours each day working with different people, looking at our models, making sure things are going well. Always have different experiments going on to see if a new model's working better or not. And then also, being at Google is very software engineering oriented, so we have a lot of services that we have to maintain as well. So it's not just all ML for us. That we maintain a pretty crucial service, even though you might not think support or Google Help is a very popular thing, but it is particularly for like average customers. They are what pays Google's bills, so we want to make sure they have the support that they have. So we have pretty fairly important services that we work on. So there's a lot of systems engineering. A lot of maintenance, monitoring, making sure things are available for our customers, and if not, then developing the tools we need to quickly restore our services. So there's a mix between ML and systems maintaining, systems development. The hours are fairly loose. It kind of feels like grad school in that sense. No one's seen to make sure you're there from 8 a.m. to 5 p.m. It's kind of like on a weekly basis, you check with your manager once or twice a week, make sure, the things you're working on, are you making good progress? A lot like, my meetings with my PhD advisor when I was in grad school. So in that sense, it feels kind of similar to grad school. That being said, people keep a pretty good structure to their schedules. Yeah, I think that's about it for me.
At work, I mainly look at conversational interaction models. So suppose there is a virtual agent that you want to talk to, or how do you establish a very human-like dialogue with something that's a virtual character. So I look at all parts of that. Some of the work is in speech recognition, which you are more probably familiar with, but a lot of the work also goes into dialogue modeling and understanding how to respond to certain kind of queries. So the work kind of spans both the deep end of machine learning, the deep learning approaches, where you can leverage a lot of data, and also knowledge-driven and kind of handcrafted, where you actually need more input from the creative side of it, where there are experts who really know how to design these rule-based methods for branching out conversations. So I would say specifically in working on machine learning, most of my time is actually spent on data cleaning. It's the boring part of machine learning, but it's a very, very essential. I would say I spend over half my time making sure that the data I'm cleaning, and nowadays you have very data-hungry methods, so you have to come up with very innovative ways of mining them or augmenting them so that you can kind of use more of the, you can kind of increase the size of your data set by using smart tricks. So I think that's what most of my day looks like. And then obviously there is machine learning training, and then a constant iteration of evaluating it, putting it into the actual real world implementation, and then testing it, and then going back to the drawing board and again repeating the process. So yeah, I think, yeah.
So I have kind of several roles. The majority of my job is consulting. For the past 7 months, I've been working with one research group at a chemical company and helping them to develop a deep learning approach to help with their chemistries, their challenges at their company. So that's been a full end-to-end project. We're kind of wrapping up the tail end of it. So that's gone from, the early on, the first few months were preparing data sets, looking at state-of-the-art models, figuring out which models are likely candidates for the approach we wanted to take, trying these models out, tearing them apart, reading the papers, and then trying to match up what the papers were saying with what the architecture was doing. So really trying to understand what it was about these models that were making them tick. And then finally, most recently, developing our own models. So new approaches, developing entirely new approaches to doing, solve the problems that we're trying to solve, which are related to chemistry. So a majority of my day in the past few weeks has been tuning a new model. So this is literally like on one screen I have TensorBoard and watching loss curves and deciding what the next runs I'm gonna kick off. You could argue maybe I should be using some kind of hyperparameter optimization like grid search and not worry about it, but that's what I'm doing. Hopefully that will turn into writing a paper. So that's probably 50% of what I do, and the other 50% is kind of spread between helping on a much more narrow scope or at least time box. Somebody says, I want to get started using a GPU for either accelerated computing or machine learning, and helping them kind of briefly, quickly, like in an hour meeting or a couple hour meeting. And also I focus on the research universities, so going to different research universities and putting on 1 day or 2 day workshops, doing introductory accelerated computing, like CUDA programming, OpenACC programming, like GPU programming, like low level, and introductory machine learning classes like Intro to Computer Vision, but in like a 1 day workshop, not like a theory heavy. It's more of a like, let's get you just started doing computer vision.
So I'm still a PhD student. So as a PhD student, I'm doing two main things: research and teaching. So for teaching, you'll probably like lead a discussion section. So that just involves, creating some slides and things to go over, or, answering questions or doing office hours or grading. So that's pretty fun. And then on the research side, that can involve, maybe just you're at your computer trying to work on a new idea, trying to debug something, but then it also involves a lot of writing. If you're writing a paper or something like that, you got to go over it over and over and over again and make it sound, like you're not crazy, which is, a long process. So there's that, and then, I always try to read something at least for 30 minutes a day, a book or a paper or something like that. It's important to always be reading, trying to learn something new. And then during the weekend, I try out some new algorithms. So just, I saw something online, try it briefly just to, try it out. Maybe I can use it in my research. So you have a little bit more freedom about what you do with your time. You can kind of dictate what you do and when you do it, but you have a lot to do, so you kind of have to be very judicious in how you manage your time.
When grad students say that they have a lot to do, it always makes me smile. So I have plenty of roles, I guess. The most important one is getting people to do research and doing research myself. what that usually involves is mentoring, usually maybe 4 to 5. Can you hear me?
Technical difficulties.
So I supervise usually, or most faculty supervise maybe 4 to 5 students, but there's a huge variance. I think goes up to maybe 7, 8 PhD students sometimes. 15. Okay, well, yeah, there you go. And part of maintaining such a group is being able to support them just purely financially, which involves a lot of fundraising and things like that. These are the sort of things we never want the grad students to ever worry about. And so that's one of professors' role, is to make sure you're talking to government agencies, industries all the time, making sure that there is enough funding for your grad students to have a, I guess, satisfactory life, not a very pleasant one, but yeah. And so part of that involves writing a lot of grants, so not just presenting stuff, but writing a lot of it, but also reviewing. So when the government wants to give money to somebody else, they want feedback on, is this a good idea? So they send over stuff to me, and then I have to give feedback. So yeah, at a very high level between groups. And then when it comes to actually doing research, the grad students do the brunt of it, most of it pretty much. But you still want to make sure that you read at least as much as the grad students do, or the union of everything the grad students have read. You should have read at least that much. And you're sort of prepared to give them feedback, which involves not just reading papers, but knowing enough technicalities about what's happening on the ground level to be a useful advisor. So that involves being up to date on everything, even though I don't get much time to code for research, knowing what is difficult, what is hard, so that you can be an effective mentor. And then again, reading papers also accompanies reviewing paper, and I think Forrest probably does a lot of this also. You want to make sure conference get the best papers. Who are the judges? It's people like me and Forrest who are giving feedback. So paper reviewing actually ends up taking quite a heavy chunk of our time. And you do more of it the more senior you get. But that's all research. In terms of teaching, I think it must be pretty obvious to you, like some of us put in a lot of effort in making sure the lectures are pretty good, assignments are strong, and things like that. Grading is fair. If you have personal individual problems, we try to deal with them as well. And then there is this another side of our position that's completely invisible, because what people don't realize is that university is kind of like a company in some sense, but we don't really have a business side of things as hires. We don't really have an HR department or anything like that. So a lot of that work also falls onto professors. So we have all these committees to decide who to hire, which students to admit, which courses to offer, how much salary increase should all the grad students get, how much health insurance should be given. All of this stuff is one part of what professors also contribute to. It's not I don't want to make it sound boring, but it is it's a small chunk, but it is a non-negligible piece of information. So yeah, this is a quick sort of view of everything that professors end up doing. So.
In your opinion, which application of machine learning will be the most significant over the next 10 years?
So the current trend is saying deep networks, recurrent networks, all these different types of networks. Those are definitely the big craze right now, and I think that's going to probably hold for a while going forward. We've seen some large advances in, this research. Neural networks were a big thing back in the 80s when we didn't have much computing power. Then it kind of died out, but now that we have pretty massive computing power, they're coming back and we do some very, very good things with them. Different applications for these, the networks becoming are things like, there's speech recognition models that become very large, right? Especially if you're trying to make things more voice command, right? All these smart devices in our homes, voice recognition is pretty critical there. The self-driving cars are becoming, there's a lot of research being put into that. So there's a lot of feed networks there, a lot of image pattern recognition is there. let's see. Big data is also a term that's been, kind of hot lately. This dealing with massive amounts of data, right? As the web becomes more popular, more people are using the web, it's become more accessible, right? You see toddlers with iPhones now, right? Going on the web, doing whatever. So much more data is coming in just naturally. So making models that really scale to just the sheer amount of data you have, I think research in there is pretty big going forward. Yeah, I think those are. Yeah.
So this might be a little biased based on what I work on, but so we've definitely seen speech recognition accuracies really go up in the last few years, and that's because that's driven by the need to have an easy way to interact with our devices as they get smaller and smaller. I think one gap in that knowledge is actually understanding, so we can get to what people are saying, who is saying it, that's things like biometrics, but an algorithm still doesn't understand very well how they say it, and that's a big part of human communication when we talk to each other, and that can make all the difference in a natural interaction. So I think the next big development in the future should be on focusing on human behavior understanding, and as more applications come up in healthcare and related areas, I think that will become really significant.
But I mean, first, I think there's no doubt that AI and machine learning are going to have a huge impact everywhere. It's going to touch everything, everything, self-driving cars, all the applications you can imagine for computer vision, autonomous farming, and speech recognition. But in terms of significance, I will also be biased from my personal background. And as important as it is for Siri to understand us, I feel like in terms of significance for how this is going to positively affect humankind, I feel like some of the most important applications are probably going to be in healthcare, and you're starting to see this in medical imaging, where computer vision is being used to interpret MRIs. I also think there's room for, there's clearly going to be developments in robotic surgery, ophthalmology, and also in the biochemistry side, sort of the molecular side of medicine, where there are going to be deep learning approaches developed for making connections between, well, I'm definitely, this is stuff you're working on, so I'm not going to steal your thunder, but the links between what's encoded in our DNA and disease, between DNA and three-dimensional protein structure, between the protein structure and molecular contacts. These are all areas I feel like are ripe for machine learning types of approaches, and will hopefully positively impact humanity.
I don't think this one works. Can we borrow yours?
Yeah.
Should work now. Oh, it should work now.
Switch.
Okay, thanks. So to be honest, I really don't know what methods are going to be. You want to say you do know, but I really don't know. But yeah, like what he was saying with the protein structure prediction, that sounds like it's going to be a big deal for the next, I don't know, few decades. But I really don't know. But what I find interesting is what's going to happen when quantum computers start becoming, more manageable. How's that going to affect algorithms? Are there going to be cool new algorithms we can do? I don't know. I mean, yeah, just to be honest, I have no idea.
I kind of agree with Forrest on this one, actually. It's very, very difficult to know what the applications of machine learning will be successful. Nobody can foresee easily what problems are going to be easy, what problems are going to be difficult, and especially sort of for me, I have to kind of decide what the next generation of PhD researchers is doing. It's a problem we struggle with a lot. That said, again, everybody's been talking about what they work on, so a lot of my work is on natural language processing, and I don't think it's an application that will necessarily we'll succeed at, but it's one that we are very, very bad at right now, or by we, I mean us machines. So machine learning is not really very good at natural language processing. It's been getting better, but it's one of those things, like language is something that makes us very different from animals, or sort of the complexity in our language is very different. And so for me, it's a personal nut to crack. Like, can we get machine learning to understand language? And that I think will opens up a bunch of applications, but also is one of those things that machine learning is not very good at right now.
Awesome, thank you. So we're going to open up to field some questions from the audience. We have a few mentors that have a microphone that'll run to you if you have a question. So, yeah, just raise your hand if you have the first one. I know James is the winner. Hey, Sam. James, right down the floor.
How were you able to find your first job in machine learning? How did you manage to find your first job in machine learning?
Maybe I can take this. I perhaps have the least related background, so maybe, is this working? Wow. Hang on.
Are there any computer scientists?
Working on it. I feel like we made great advances in technology, but like the two things that are like so far behind are like printers and like sound systems and like PowerPoint presentations, right? I feel like we have not advanced at all in these.
All right, so maybe I can just speak up. So my background is probably the least likely, I think, out of all of us to be in machine learning. So maybe I'll just share my story. I've been interested in machine learning for a long time, but I'm coming from chemistry. And so I would consistently choose problems. Obviously, self-study and learning these things and reading and working on models in my free time, certainly. But I was in grad school and a postdoc, and so I had other responsibilities that I had to do. But I would consistently angle the types of projects that I would work on, the math that I would study, the computer languages, the libraries, everything. I would always try to find excuses to use or learn or do things that were tangentially related. And finally, I was in a position to sort of start doing some developing predictive models for atmospheric dynamics for satellite communication. Doesn't really matter. The point is I finally got to a place where it really made sense for me to take a machine learning, a full-throated machine learning approach to the problem that I was working on. And that ultimately, I think that project in particular ultimately opened the door to getting a job at Nvidia. So I hope that was helpful.
I think for me, machine learning kind of came from trying to think in detail about the problem. So one of the things you do in PhD is you try to really narrow down your hypothesis about how you think something, let's say you're looking at certain kind of data, and you formulate a hypothesis of why you think the data looks the way it does, and then try to use that fact for predicting or generating something. And I think that's where I started looking at machine learning first, to actually technically express in math some of the hypotheses and ideas I had. And apart from that, in terms of just practicing machine learning, I would say I would participate and push in myself to participate in a lot of machine learning challenges at conferences, or nowadays you have a lot of online machine learning challenges, and that kind of gave me the breadth of experience. So when I was going up for my first job, although my PhD thesis wasn't something very narrow, I could talk about these number of other things that I had looked at and had some experience, some familiarity with, where I could get started, and that I think was very helpful.
So I think you guys talked. This okay.
Really works.
Yeah. So yeah, I think the theme I'm seeing is like getting a lot of practice in, finding out what's interesting to you, trying to get try to learn as much as you can outside of just the coursework, right? If you're interested in machine learning, try to develop different types of models for different toy problems. Try to get the experience and knowledge of just different types of models or just the research in the area. And then the other thing I'll say too, as you're in school, and I'm going to be very biased here, try very hard to do an internship at any type of industry place, whether it be Google or Yahoo or Microsoft, Nvidia, whoever it might be. Internships are great for getting some, applied, getting some experience in the field, both in machine learning or just software engineering in general. And it kind of gives you a good feel if you like that type of work or not, right? Before you go into a full-time. So I'm very biased in that opinion. I think internships are a very great way to go, and I think if you develop an interest in machine learning, working on different problems in there, I think that makes your application for doing internships into one of these kind of industries much more what's the word? I think it definitely helps to get into like internship type position, which I would definitely advocate trying to do before graduating.
It's not going to be a very useful answer because I've been basically doing machine learning pretty much the whole time. So I guess 15 years, 16 years now. So I'm lucky machine learning took off because I wouldn't have a job if it didn't. So yeah, and just to talk a little bit about the transition or how I started, I was mostly doing sort of playing around with robotics a lot in my undergrad, and always sort of frustrated at like mechanically we can make it do things, but from an intelligence point of view, it was, they're still not very good in terms of what robots can do. So just trying to think about, hey, maybe the software side is a lot more interesting because there are clear challenges. So that's where I got started. Yeah. I guess Forrest doesn't have a job.
Relatedly, what are the frameworks and technologies that you use the most in industry?
You want to start again?
Sure. So working at Google, it's mostly TensorFlow. Developed in Google. So most of our machine learning is done through TensorFlow or something very much like it. And then, if not TensorFlow, then some other type of distributed framework for doing basically matrix multiplications on the cloud, right? I think it's like Facebook's called Torch, I think.
PyTorch, yeah.
PyTorch, that's another framework. So something analogous to that, I think, is the big trend right now in industry, at least from my experience.
Yeah, I think for me, whenever I'm doing deep learning, I'm using PyTorch, TensorFlow, Keras, these kind of things. Things I'm pretty sure you're all familiar with. But once in a while, something needs to be more computationally efficient, like speech recognition, for example, is not something that is ideal to run on a deep learning engine end-to-end. So you would use more customized code, and there are many open source alternatives. And I think depending on what you're interested in, it's a good idea to just have a general know about what is popular right now in that open source community. So for example, for speech recognition, we use this toolkit called Caldi, which is based on top of actually FSTs. And there are parts of it that are deep learning, but the whole effort of having that toolkit is have a seamless system that can blend in all the existing parts with modern deep learning approaches. And
as far as the software stack, probably nothing surprising. TensorFlow, PyTorch for the frameworks. The specialized libraries, in my case, I'm doing a lot of chemistry, so there's a library called RDKit that we use a lot. Certainly, I think worth mentioning is NumPy, SciPy, Pandas. Being really comfortable in NumPy is awesome. It's really powerful. And maybe a not mentioned yet part of our stack is, and one I think is kind of exciting to me, I come from computational chemistry, where we use research computing, high performance computing type of infrastructure, and scaling up machine learning models to use HPC resources is kind of exciting. And so there's a stack that we've adopted to do that. So we tend to work in containers, and the schedulers that typically run on HPC resources are things like Slurm. So that's the scheduler. So getting containers to work on multiple nodes in an HPC resource. So anyway, the point is that Docker features prominently in our stack, as does Slurm, yeah, I think that's those are the other pieces I wanted to mention.
We're not industry.
Oh, okay. Not industry stack.
Grad students of this.
What approach do you recommend for understanding machine learning from the ground up mathematically? If you can understand that with the reverb.
Maybe some, well, I'll start. Personally, I think there's no substitute for coding it up yourself from scratch. And Keras doesn't count because you can do a lot in very few lines. Well, for example, NumPy is pretty low level though. I mean, if you can code up a neural network using only NumPy calls, you probably understand the concepts. So that's what I would say.
I would say the most important skill in this field is what I kind of call machine learning debugging. It is the ability to understand why your model is not behaving the way you expect it to behave and tweak a few things. And so there's no real replacement for learning it bottom up. I think I would again give the same advice, but instead of saying, talking about coding, I would say work on a lot of different problems to look at challenges, like I said, and try to apply something that you think works and see it break, and then try to work from there to figure out what is the minimum thing you can change in your code or in the model that you're suggesting. So somewhere maybe you're trying to use a recurrent architecture where a convolution architecture would have done a much better job. And to understand your domain and your data, why in this specific case it makes sense to use this. And I think that experience is invaluable.
So I don't have a great answer since I kind of went through the graduate program here, which was really good in terms of giving you the background on the math and stats and all that. But what I would say, definitely what you're saying, with coding things up in this something like NumPy even, start with something let's build gradient descent to optimize some function. Trying to just understand the building blocks of how these models work and just coding it up yourself and trying to piece things together, I think goes a very long way. And then I would say some general math classes I think would help if you have time to fit it in, or if you try to go for a math mind or something like that. I think stuff you learn from linear algebra is very important. A lot of these things boil down to different types of matrix multiplications or different manipulations of matrices. So understanding linear algebra is very, I think, helpful for understanding kind of like the theory behind machine learning, and then probably some kind of some entry level like stats courses. Maybe it might not be so much into the model, but just understanding like how do you analyze different data sets as a whole. Trying to kind of get that core understanding. So I would say like if you could fit in the stats, I forget what it is, if it's 201, 101, and like a linear algebra course, I think those would be the two probably strongest types of courses you could take to kind of help understand some ML concepts.
I was also going to say that it's important not to get too caught up in all this, deep learning, let's just throw a deep neural network at it. I really agree with what Abe was saying about coding it up from scratch. That's really important. But, when you're coding something up from scratch, think, why don't I try k-nearest neighbors? Why don't I try a decision tree? And, see which one works better. And you'll be surprised. A lot of the times, depending on what data you have, k-nearest neighbors is like, could be the fastest, most efficient way to do it. Or, on some other data, deep neural networks could blow everything else out of the water. So it's important to really understand the machine, what machine learning is. You should really understand all these other methods and understand where they're effective and where they're not effective, and where deep neural networks fit in this whole framework, this whole field.
So I would agree with what everybody said. I think I might just add some small addendums to everyone. I think statistics specifically, you should be thinking about probability more generally, and probabilistic distributions, and like how random variables work, and information theory, and a bunch of these things become relevant for understanding how machine learning works. But even pretty much all advances in machine learning has come out of this math. It's not come out of coding. So if that's part of your objective, is to not only understand but perhaps advance, it's important to know these things. In terms of coding, yes, there's no substitute for actually coding it from ground up. But one thing that I've personally found useful is to also read a lot of code, sort of see how people structure things. And partly that goes to Naveen's point of understanding when things would fail, or even just like taking an image classifier that's very good at classification, trying to figure out, okay, what about this architecture would help it possibly figure out this is a cat and not a dog or whatever. Just sort of approaching machine learning with a lot more questions like that is pretty useful. I think that's all I have.
So what do you think the role of traditional AI is going to be amongst all the craze of neural networks?
Okay, I guess I take the difficult questions. So I think things change faster than we realize. Traditional AI is, in some way, it's symbolic way of doing things. And what it allows you to do is inject a lot of information into how things should be working, right? And that's useful not only being able to inform how things work, but also being able to understand why things are working. So nobody goes away from symbolic approaches and say, I have no idea why this is doing what it's doing, right? So going forward, I think machine learning is just going to move a little bit more towards sort of embracing those core needs. Like we need to be able to learn from very little data, and that might involve introducing inductive bias, which is most easily done in some symbolic form. Also, we need to know why things are doing what they're doing, and sometimes that also leads to symbolic stuff, right? The other reason to do this is because deep learning, and there have been different people trying to measure this, they feel like the deep learning is plateauing in terms of how much more capability we can do with it. And in fact, the applications are growing exponentially, and they'll grow for a long time. But in terms of just sheer prediction power and in terms of intelligence or reasoning, it seems to be plateauing. And I think the next level of reasoning requires you to combine the notions of symbolic, like just the fact that we can add two numbers pretty easily, but for a deep learning problem, that's not a easy solved thing. How do you combine both of these views to sort of create interesting systems? Think a bit more.
Anybody?
So my question might skew a little bit toward Forrest and Professor Singh, but now that machine learning graduate school admissions are getting outrageously competitive, do you have any advice for students trying to enter into academia for machine learning?
Yeah, that's a. We are going through that right now. We're looking at applications, and it's just to kind of give you some rough statistics. Maybe depending on how you count, out of the 40, 50 faculty we have, maybe 10 to 15% are machine learning, maybe 20% if you say AI, and about 60 to 70% of the applications for PhD are for working with one of us, which translates to around approximately 600 to 700 applications, right? Unfortunately, what that means is we don't have the time to give everyone the attention we would want to give. And this is the case in every university. And so we end up relying on simple metrics. So things like you have to have a good GPA, right? Like that's just a filter to make sure that helps us go from 600 to maybe 100 or something like that, right? And in some sense, it's valuable because it shows that not only are you hardworking, but you're able to learn things. And I mean, you can argue whether GPA is a good metric or not, but good GPA usually means good things. Bad GPA may not mean as much. At least my GPA was really bad at the undergrad, so I wouldn't have gotten into a PhD program. But I think the other thing we look at is how sort of motivated you are to do research, and partly that is informed by how much research you have done, because research is a very difficult thing to do. There's a lot of reading involved, there's a lot of struggling with writing involved, a lot of failed experiments, a lot of working on an idea for 6 months and then finding a paper that has done exactly what you've done, maybe back in the 60s or something if you're extremely unlucky. And so if someone has shown evidence of going through that process and maybe has a paper at a conference or even a workshop, depending on where they are, right? So if somebody is a student at a top research university, I expect them to have attained a little bit more. If somebody is at a liberal arts college and they have a paper that's extremely impressive because their professors are likely not engaged in research themselves. So yeah, research experience and GPA ends up being our sort of thing. So you can translate that into whatever suggestions you would have. Yeah.
So I did my undergrad in electrical and computer engineering, so I wasn't exactly computer science, and I applied to a lot of PhD programs, and so I got into a few programs. The one I really wanted to get into was the PhD program at University of Michigan, but I didn't get into that one, and I got into the master's program. So I decided to not go to the PhD programs I got accepted to and actually do the master's program at University of Michigan, and there I got a lot of experience in research in machine learning, and I published a paper, and it was great, and it made me get a better idea of what I wanted to do, and so then I could apply to PhD programs again, and so I got into the PhD program at University of Michigan and also the PhD program here. I ended up deciding to come here, but it doesn't have to be you go to the PhD program right away after your bachelor's. Sometimes you could do a master's and then publish a paper or something like that. And then when you apply again, you'll be a lot more prepared.
I just want to add to that. It's good goal to have PhD, and definitely we want people to do research and advance the field, and I want to encourage people. But just be aware that PhD is not everything it's made out to be, and so it might sometimes be, and often is, a wiser choice to not pursue PhD, but actually get a master's degree and actually have much more of an impact in the real world, which is as important, if not more, sometimes, instead of trying to pursue a PhD. So. Especially given the demand and stuff, there is a lot of randomness involved. So yeah, don't let it discourage you, and don't be just single-minded about it.
So one thing I'll add to that too. So something that helped me, this was back in 2009, so I don't know if it's applicable now or not, but my PhD advisor had reached out to me before I got the admission, the acceptance letter, and he said something that really helped, at least him, with my application was I had done some stuff as an undergrad trying to do what I can with like ML, you know, whether it be like just working on a project that a professor was doing or doing something for the summer, working on some project. And, you know, in addition to the GPA and stuff like that, I think showing interest in the field on your own, doing like, you know, you're having some initiative in whether it be working with a professor in some manner or other students or just on your own working on a project to do something, I think would really helps with the application.
I'll just add one thing. Perhaps departments outside of computer science are also possible candidates you might consider. There's a chemistry lab at Harvard that they're focused entirely on machine learning. There's a physics lab at UCLA that's doing particle physics, but they are working on ML approaches to particle physics. And so there are these, perhaps certainly all over medical imaging. In the medical schools, there are researchers working on developing instrumentation, studying I guess, primarily MRI, so these tend to be neuroscience-focused groups. Point is, there are all these research departments outside in different domains that are looking to apply, so maybe those are worth considering also.
I guess this question is more for people in the industry. So how important is a master's, and like also do you have to have a thesis if you want to go in the industry for AI?
I guess it depends on the role you're looking at. So if in your industry role you're looking at developing new models, I would insist that you have some firm foundation in the mathematical techniques or understanding how things work under the hood. There's totally a different side of it, which is implementing things at scale, which is probably something that Abe might refer to in his daily work routine, and that is also a very important part of machine learning. And I would not necessarily insist that might need a master's degree. So it depends on, again, what you focus on. So a career in machine learning is not necessarily one single thing. There are multiple different approaches, and you can choose what is best for you in that way.
So, say in my experience, I worked pretty much in ML throughout my time at Google, and on our team we have people that range from undergrad to master's to PhD. Whether that be even in computer science, we have someone on our team that joined Google because he started developing a website for his church. We have people from all different types of backgrounds, but I think, as I say, it kind of depends on what type of work you want to do with ML, right? If you're implementing models to solve problems, then you might not necessarily need a master's to do that. If you're interested in more of like a researchy role, trying to develop models to solve new types of problems, then that's maybe more like a master's or PhD might give you more of an edge. So from my experience, it's all broads of the educational spectrum.
We have a program at Nvidia called the New College Grad Program, and it's specifically for hiring people right out of their undergrads. And and just to echo it, I totally agree. It depends on how you want to, what type of machine learning you want to do, whether it's more of a research-oriented role or an applied role. In the New College Grad Program, you would be very quickly exposed to a lot of applied machine learning, but with a few years, maybe getting your foot in the door with the New College Grad Program, spending a few years working on different applied projects, rotating through some of the different departments and interacting with our Nvidia research, then you could eventually, if that was your goal, ultimately end up in the research department doing pure ML research. But there are a variety of ways to do ML in industry. So, yeah, just no industry.
What do you think the role of AI and machine learning can be in facing global challenges such as climate change?
This is just off the top of my head, but I mean, if you were looking for polluters from satellite imagery, maybe you could analyze satellite imagery.
So think about that Microsoft commercial about the agriculture and tackling with AI. I don't know, I saw on Hulu, I think. Anyway, so I think AI and ML could come into these type of problems because I think it becomes like an optimization problem or an efficiency problem, right? Like taking the agricultural one for an example, right? How can we make the most of the land that we have with the water that we have to make the most crops that we have, right? That could be, and that's an optimization type problem, right? That you could probably throw ML at. You know, like with the transportation issues, you know, they're using ML to tackle like the self-driving cars, or you know, I'm sure like, you know, once that gets more traction, there's probably, you know, that could have probably pretty big implications for public transportation, right? You know, making things more efficient, getting people where they need to go faster and stuff like that. I think, yeah. So I think if you can form it as a optimization type problem, you could probably attempt to throw some ML at it.
I think also predictive modeling to see the outcome of different approaches before things have actually happened, to have like a convincing argument, because when you're trying to model something as sophisticated as like an ecosystem and look at different factors that affect global warming, I think that's something that AI could probably help with.
You know, there's this program MAPS here at UCI that tries to merge, you know, the natural sciences with artificial intelligence, and they do some really interesting research. There's some on like forest fires, like trying to predict where it goes, but then there's also atmospheric modeling, and I can't remember all the projects, but some are related to like glaciers shrinking and water levels rising and things like that. So it's called MAPS here at UCI.
What global warming? I'm just kidding. Yeah, sorry. Yeah. So yeah, like a lot of the, like what Forrest said, just kind of adding to that, there are a lot of stuff I've seen of machine learning to climate change problems has been to identify sort of how bad it is, or how it's changing, or how can we make it easy to detect. Like, so forest fires is one. I'm working with some geologists on like how fast sort of the icebergs are melting and things like that, right? So how bad is the situation? We should have a good handle on it. But to be honest, I don't think the solution is that complicated. Like, the solution has to come from governments and sort of policy, right? Like, and some of those things you can't quite solve just because you can do a lot with machine learning, right? So I feel like we are trying to do our best to sort of quantize how bad the problem is, or quantify. But the solution is pretty simple in some sense, and yeah, it has to just come. Everybody has to agree on it. Yeah.
So, if you are somebody who's really interested in the pure research aspect of AI, how important is a master's, and is it like, can you go into industry and find somewhere that's like some fascinating cutting edge research is happening, or is it like stick to the universities? Like,
I can start a little bit. So, I mean, partly I sort of considered at some point going to the industry and pursuing a research career there, and I'm sure Forrest is also in the middle of considering that. So, Okay, so I think a master's is kind of required because you need the fundamental mathematical background that unfortunately most undergrad programs don't cover. Including at UCI, we try it, but by the time you have enough courses to take, even the basic machine learning, it's just kind of late. So a master's that allows you to go a little bit in depth into application areas or the mathematical backgrounds is kind of needed. Other than that, most active research groups in the industry, at Nvidia or Microsoft, Facebook, Google, they usually recruit PhD students, but they often have master's students in the group which have sort of a more research background. Sometimes they call them research engineers, something like that, that are more in charge of doing some of the software development work. It kind of varies across companies, but that's a good approximation. And so I know some people who never have a PhD, but because of being able to get into this group, they're able to have a somewhat interesting research career. It's very rare, both because of luck and because of the training that PhD provides you is just not something you can get, right? Even after a PhD, there are arguments to whether you want to do research in the industry or not. And I would say I tend more towards the university system, but yeah, that's my thoughts.
Yeah, I think I heard two questions. One, do you need a PhD or master's, and whether industry has a suitably pure research environment. At least on the second one, we certainly have a research team, Nvidia Research, and we publish and do research, and it's a pretty pure pursuit from that perspective. And certainly, I mean, Google, Disney Research, I mean, Facebook all have similar wings. As far as the master's PhD, I think you could. I think there is a viable path, as I was mentioning with the new college grad program, to getting there without a PhD. But I think a master's or PhD, if you're going into pure research, master's and PhD programs really teach you how to approach problem solving, how to think critically. There's something very special that you get out of a PhD program, and it's a little bit tough to quantify. I think you could argue you could get some of that in a non-academic, non-grad program, but I don't know. I think if you're really interested in pure research, a PhD is pretty special, I think.
So I think I agree. If you're going to be like hardcore researching, I think, master's or PhD is very useful to have. It'd be pretty hard to get it, at least right off the bat, without one. That being said, I have seen some people take it. So something that you could do if you don't have like the master's background, I've seen people do is I have a friend that started at Google as a front-end engineer, and then he eventually moved to DeepMind, working on front-end applications there. And after several years working with him, he's now starting to get into kind of like a researchy type role, which is what he really wants to do. I had someone on our team, he was also, working as a back-end engineer on an unrelated project, and now he's doing kind of applied ML with me on our team, with hopes of eventually going to like more research type position within Google. So if you don't have the master's, I would say it's not impossible, but it's going to take some time and trying to get working in like the related teams and trying to get at least a lot of experience within the industry on a related part of a team doing that to get in. But it'd certainly be a lot easier to get there. Yeah, certainly if you had the master's or PhD.
Are there any more questions from the audience?
By the same token that many tech companies have, Google, for example, projects are prototypes in Python, and then they may be translated to C or some other lower level language for optimization. Do you think that Python is the most optimal language for doing machine learning? And what do you do you believe that Julia computing, if you're familiar with that, might supersede Python for these purposes?
So I think Julia was just being developed when I graduated, so I don't have much experience in that. It's hard to say with Google. We just throw a ton of computing resources out in the cloud, and it doesn't matter if it's in C or Python. Anything that you write in Python does get converted into C operators in the cloud. So in that sense, Python is more than sufficient to do machine learning. Now, if you're working on like the hardware component of it, or if you're trying to work on kind of more the production aspects of machine learning, then probably you'll want to know more of the C or C++ to kind of work with the hardware a bit more. But I think certainly if you have pretty solid understanding of Python libraries for ML, like whether it be TensorFlow or NumPy, SciPy, things like that, I think that would be pretty sufficient.
I think unfortunately I do not have a very good answer for that because so before talking about languages, let's talk about different packages that you use, and we see this trend that the thing that is necessarily the most efficient is not the most popular. And because we're working in deep learning and modern machine learning is a lot of open source community based things, people tend to gravitate towards things that are popular, and then by the time something else efficient comes up, the crowd might have already moved over to something else. So I think in general it's a question of the trade-off is between, do you want to work and put out your code into something that is very obscure that maybe in the future will catch up, or do you want more people to be looking at it? And at least as a researcher, I would want my code and my research to be more peer reviewed and more accessible to as many people. So that's my bias towards that.
I can't comment on Julia, but I will say something about Python, and that is, at least for the deep learning frameworks, and it's slowly becoming the machine learning algorithms also. Yes, you're usually you're coding in Python, but on the back end, these are making CUDA calls, often cuDNN. Or other lower level CUDA library calls under the hood. So yeah, Python is definitely slow, but the implementations in the frameworks are fast because it's just Python calling CUDA backend calls if you're using GPU.
Yeah, I appreciate how easy Python makes things. I have some issues with the language itself. I just don't think we should use dynamically typed languages, but I've programmed in Python for deep learning, Python, C++, MATLAB, R. R is a terrible language. MATLAB's not too bad, but there were some nice things about doing C++ because you could optimize. Like when I'm doing certain things in TensorFlow, the way they do the backpropagation is really suboptimal because they, do it a certain way. And when I was doing it in C++, I could actually say, this is how you do backpropagation and save some memory or something like that. So there are ups and downs to everything, but Python, it's really nice. It makes things really easy, but it's not like a big kid language to me, at least,
So I'll just tell you a little quick story that kind of relates to what a lot of people said. So when I started my PhD in sort of 2008, I had worked with Python for a couple of years, but there was this new language called Scala. I don't know, has anybody heard of it? A few of you, right? And I basically fell in love with the language. And at that time, it was so early that we were reporting compiler bugs to the guys who were writing it, and things like that. And it was 0.06 or something that we started with. And but for machine learning, it was perfect. The syntax and things like that, it was purely functional. It was strongly typed. The things that I liked about languages, and almost as a lab, we had bought into Scala being the future of machine learning, and we were not sort of unique in that. A bunch of like high-profile machine learning people had bought into it, and it sort of, I still believe, like in terms of syntax, in terms of ease of writing stuff, there are lots of benefits that other languages provide on top of Python. But what eventually changed the tide, and I realized that it's not so much about the beauty of language, but about how much you make it available to people in terms of libraries and packages and support for different platforms and things like that, that clearly Python has really taken over, right? And so what is the best way of doing things is not always a clear answer. It's not over like mathematically or syntactically what's the best way. It's very pragmatic. What is the thing that will get you what you need to do the fastest, right? So.
All right, so that wraps it up for our panel. Thank you all so much for coming, and thank you to the panelists for coming. Can we have a round of applause for that?
Thank you so much for taking the time to do this for us. I know that all of us appreciate it, and hopefully see you next quarter or the year after if we're still here. But thank you so much. If you need anything else, just let us know, all right? Thank you very much.
Thanks for having me.
Thank you.
We should also give a hand to the hosts.
Yeah.